In statistical physics, we want to study the physical properties of macroscopic systems, so systems that have a very large number of atoms or molecules. And we want to understand how these physical properties come about from all the microscopic parts that make up those systems. So my first question is, what do you call the complete description of the microscopic state? For example, if you could describe the speed and the position of every single particle at a given time, or if you had a complete wave function of the system. That's called the microstate. Now, what do we call the macroscopic state, such as the total energy, temperature, and pressure? That's the macrostate. Now let's look at how the microstates and macrostate relate. How many microstates are in a given macrostate? What's that called? It's called the multiplicity. Sometimes it's called the statistical weight. Now, in a particular situation, you might have some microstates for n particles, and each particle has just 2 possible states. How many microstates are there? There are 2 to the power of n microstates. What is the multiplicity of each of these states? Well, we get it from combinatorics. It's the number of particles, big N, factorial, divided by number of particles in one particular state, little n, factorial, times factorial of the difference. Now let's consider an isolated system. An isolated system is one where the total energy is fixed. The system can't exchange energy with anything else. Our total energy is constant, it's conserved. For such a system, what's an alternate measure for the multiplicity? It's entropy. The entropy is Boltzmann's constant, K, times the log of the multiplicity. So for an isolated system, what's the most likely macrostate? The most likely macrostate is the macrostate with the maximum multiplicity, or the maximum entropy. When an isolated system is in that state, we say it's in equilibrium. What about the most likely microstate? Well, for an isolated system, as long as the total energy is enough to access, various microstates, all of those microstates are equally probable. For an isolated system, we can relate entropy to temperature. How do we do that? We take the derivative of entropy with respect to the energy of the system. And that will give us 1 over the temperature in Kelvin. So what's the probability of our isolated system being in a particular macrostate with energy, for example, E1? The probability that you find your system in state E1 is given by the multiplicity of macrostate E1 divided by the sum of the multiplicities of all the energies. In other words, the sum of all the microstates. Now let's consider a different system. So we're going to look at a system that's in a heat bath. So the energy can fluctuate, right? Because the energy can be given to the heat bath or taken from the heat bath. However, the temperature is fixed. So what's the probability of such a system being in a macro state with energy E1 this time? It's given by the multiplicity of that energy level, E1, times the Boltzmann factor, e to the minus E1 on KT. And then instead of dividing by the sum, all the microstates, we divide by the partition function. What do we call the normalization factor, which is the sum over all the energies? It's the partition function, isn't it? So if we have discrete energy levels, then we have a sum over n. So where each energy level is indicated by the quantum number n. At high temperatures, what approximation can we use? Well, at high temperatures, KT becomes very, very large, which means e to the power of minus something on KT approaches e to the power of 0, 1. That means if the Boltzmann factor is 1, all macrostates become equally probable. Now we're going to have a look at the Maxwell distributions. Let's match each equation and graph with the appropriate distribution. First, let's start off with the equations. The equation for the Maxwell distribution of speed is this term, which has, as you can see, a v squared times e to the power of minus mv squared on 2kt. The mv squared on 2 is, of course, the kinetic energy. So what about the Maxwell distribution of velocities? Well, for each dimension, the velocity distribution is minus mvx squared or vy squared or vz squared divided by kt. And when it comes to the distribution of energies, we have, of course, the Boltzmann factor, e to the minus energy divided by kt. This is multiplied by the square root of e. Now let's look at the graphs. The Gaussian curve shows you what the distribution of velocities look like. The peak is at a velocity of 0 because, of course, you have equal numbers of particles going in the positive direction as we have going in the negative direction. The distribution of speeds looks like a skewed Gaussian. The peak of this is the most likely or most probable speed. And the Maxwell distribution of energies is skewed even further. At higher energies, you can see that it falls off as an exponential tail. And it's approximated very well by simply using e to the power of minus energy on kt. Now let's revise what you can do with the partition function. One thing you can do with it is normalize probabilities. So to make sure your probability gives you a correct value, you take the probability, which is the multiplicity or degeneracy times a Boltzmann factor if relevant, and then you use the partition function to make sure that your probability is properly scaled. You can determine the Helmholtz free energy of your system using the partition function. You do this by taking the log of the partition function and multiplying it by minus kt. The partition function can also be used to find the internal energy or the total energy of the system. Again, it's related to the log of the partition function. In this case, we take the derivative of this log with respect to beta. Beta is 1 over kt. So to do this derivative, you have to re-express your partition function not in terms of kt, but in terms of beta. You can find the entropy of your system once you've got the Helmholtz free energy. So if you take the derivative of Helmholtz free energy with respect to temperature, that will give you entropy. Helmholtz free energy can also be used to give you the pressure. This time, you take the derivative of Helmholtz free energy with respect to volume. And we can use the total energy to find the heat capacity of the system. To do that, we take the derivative of the total energy with respect to temperature, because heat capacity is a measure of how much the energy in your system changes when it changes by 1 degree Kelvin. Finding the mean energy of a system is one of the things that you'll commonly do in statistical physics. How you approach it depends on the information you are given to start with. So, do you know any variables that are related to energy? If so, you can take the RMS value of those variables and relate them to the energy. For example, if you know the speed, then you can find the RMS value of the speed and use that to find the energy, which will be half m RMS speed squared. What if you know something about the energies and the probabilities? Well, one thing you could use them for is a sum. So you sum the energies, but you weight them according to the probability of the system being found in that energy. If the energy levels are very close together, then you'll take the integral rather than the sum. And that sum will be your mean energy. The other way you can use energies and probabilities to find your mean energy is to find the partition function z and then take the derivative with respect to beta. So the average energy is going to be minus partial log z partial beta. Finally, if you know the degrees of freedom, then count them up and add half kt per degree of freedom. That will give you the average energy of your system.